one second. Okay, so where we last left off, we wanted to contextualize fine-tuning relative to other techniques that are out there. I was sharing this diagram here from Andrei Karpathy about sort of where he situates fine-tuning between prompt engineering, when you would use fine-tuning versus prompt engineering. I think the other interesting thing is to contextualize it with what's going on out there from a business perspective. Fine-tuning versus, prompt engineering plus foundational models, I think are two paths that people are debating. And you can see, those of you who've read like the Google, we don't have a moat, neither does OpenAI memo. LoRA, which is, again, what we're talking about today, features prominently in the memo because it drives a lot of these cheap fine-tuning models that we're seeing everywhere. I'll give you a brief example, advancing a bit to the slide here. Vicuna, which is this open source version of, you can call it ChatGPT, sure, or at least on par with ChatGPT, was fine-tuned on the open source Llama model using around $300, which is insane if you think about GPT-4 or ChatGPT taking reportedly hundreds of millions of dollars to train. And behind that $300 training is fine-tuning, and more specifically, parameter efficient fine-tuning. The last interesting bit is in the Google internal memo. There's this other point about there's aspirations for Google to incorporate near real-time information into these large language models. And if you're doing that, there's no way you can do a full sort of fine-tuning on top of a base model. And so that's where LoRA comes in. With that context, let's jump back into the paper. So to start, it kind of restates this problem. A lot of these adaptations to multiple downstream applications are done via fine-tuning. But the problem is that this sort of baseline fine-tuning on the existing model often contains as many parameters as the original model. So this is how I visualize it. You have this simplified view of the pre-trained weights on the left, the model weights on the right. The problem is that delta W is massive. Now, fine-tuning is not a totally new concept. But the problem the authors are saying here is that existing techniques often extend latency, inference latency on top of the existing model. And more importantly, these methods usually produced a fine-tuned model that doesn't compare as strongly against the full baseline tuning. And a visualization of what they mean here is in these existing techniques, you typically have an adapter. This adapter is probably another fully connected feed-forward neural net on top of the previous pre-trained weights. And, if say X here is like all the way on the bottom is like the input, that inference has to fully propagate in a serial manner from the existing pre-trained weights to the adapter and finally to the output. So the problem with this is additional latency. And more importantly, it's not as good as a full baseline fine-tuning.
Hey, maybe
yeah.
I can ask you something like to level, maybe even just start.
Sure.
Why would someone want to fine-tune? Like, what is the value prop of, fine-tuning an LLM?
Yeah. I think there's depending on who you ask, the answer might be different. If I'm, say, like a solo entrepreneur, indie hacker or something, and I want to build an application that isn't using one of the OpenAI models or Anthropic or whatever, I might want to take an off-the-shelf open source, let's say it's, I don't know, Flan 5 or GPT-2, but I have a very defined set of tasks I want it to do. Let's say I'm trying to build a company around translating human language to SQL. That's a perfect example where there's a lot of data out there for you to train it on. You can take an off-the-shelf open source where the weights are open source, and fine tune that for your very specific objective.
Got it. Got it. Got it. And in this case, like maybe you can help me understand. So one of the things that this paper is saying is that, well, it's freaking hard to fine tune. It's not feasible. If you have something like GPT-4 with 175 billion parameters,
Mm-hmm.
tuning just doesn't, like, could you explain just why, like, what's phenomenal about this paper is that you don't have to go and fine tune all of those billion parameters, but you can do something kind of
Mm-hmm.
in between. Yeah, what's hard about fine tuning? Maybe just walk us through that.
So the way I would say it is, let's say the world exists without LoRA or any of these for these greater class of parameter efficient fine tuning methods. You have you're choosing from two evils, and one evil is this one, which is you have your existing, let's say the pre-trained weights W is this like 175 billion parameter GPT-4 model on the left.
Yep.
And on the right, you have what your fine-tuning weight updates are. And clearly, these two boxes are the same. And so they're both 175 billion. It's extremely expensive to train. And even after you've trained it, it's also hard to deploy because the artifact is the same size. It's like, I don't know how large GPT-3 is. I think it was like 400 to 500 gigabytes. It's large. It's not really, in a software sense, a very deployable artifact. And the other evil is maybe use another existing fine-tuning technique, but you're stacking latency on top of it. Again, you can see the flow of data from bottom to the top. It strictly has to go through this new adapter neural network. And maybe I should have flipped the two problems, because like the bigger problem is it's not as performant as this baseline fine-tuning here. And those neither are really attractive options in that world. And I think if we want to jump ahead a bit, it's, the key insight is like, what if this delta W can be smaller?
Yeah. Yep. Okay. That was really helpful just to kind of set the context. All right, keep going. This is really
Cool. No, those are great questions that I think help the reading. So, importantly, these methods fail to match. Yep, this is exactly what we just talked about. Like you're trading off between two really unattractive options if you're trying to fine tune. And this is the key insight of the entire paper. And I think as a group, if we understand what the authors are saying here, the rest of the paper is kind of like, oh, duh. The key insight is that models will typically reside in a low intrinsic dimension. And what they're saying is like so what's a model? It's a bunch of matrices in some sense. And these matrices have this characteristic of being low intrinsically dimensional. And the key was they're saying, we think the same characteristic also applies to this delta W here for the weight updates, that it's intrinsically low dimensional. And that is the hypothesis to which we will use to shrink the delta W down. And again, if we go back to the original not so attractive option, this baseline fine tuning, it's going to work. The problem is just that it's really big. So what if it can work and it doesn't have to be as big? And the way the authors are trying to bridge that is saying, we think it's intrinsically low dimension. Therefore, there is a lower there's a way we can represent it that doesn't take as much memory and weights.
Got it. How, okay, keep going. I'm curious, like, how good did they get that, how good could we, if we were to represent it in that lower dimensional space, how good is that? Obviously not going to be as great as the final model, but like, is it on average like 80%? Is it 70%? Does it depend on the double? Like that's really interesting.
I mean, we can jump ahead a little bit. Let's go to the results. It's actually very astonishing. let me take you to since we had the wiki. So there's this data set called WikiSQL, which is human language to structured SQL. That was the example we were giving earlier. In the paper, these are like the baseline full fine tuning, the really expensive one that takes a lot to train. And what you see is like using this, and if we have time, we can get into it. But using the low dimensional way not low dimensional, but using this smaller version, this trick that they found to represent the weight updates in a much like magnitudes and magnitudes smaller, like insanely small. It's actually better than what the baseline was.
Wow.
And yeah, so it's one of those techniques and results and in computer science. It's just like amazing. You don't have to trade off anything. It's even better than what your baseline was, and it costs magnitudes less time to train and deploy.
Do you think that what do you think the possibility, like what do you think this applies for companies planning to deploy LLMs? Like, do you think that this means they'll use LoRA to optimize their LLM on certain use cases, and it's way, is this method, do you kind of predict this method's you're gonna see more of this, more than fine tuning for sure, but yeah, what's your take on that?
I think it depends. That's a complicated question. I think it depends. I think it depends on what you're trying to do. If I'm, let's take the sole entrepreneur thing.
Yeah.
If I'm starting a company and I'm trying to build around a feature set, I probably wouldn't reach out for fine tuning like right away. I think at the end of the day, let's go back here. In that initial stage, I would probably be spending my time in like the zero shot, few shot prompts
Mm-hmm.
area. And I think the graph is kind of a useful way to contextualize, fine tuning versus prompt engineering, few shot prompts. But I think it's actually kind of like an exponential x-axis, right? It's significantly harder to figure out fine tuning than it is to write a few sentences. So
Yeah.
if you're a new company, I would probably stick there. I think if you're a larger company that, let's say you're an established player on like internal dev tools or something, and you want to roll out let's just stick to the like the human to SQL thing, and you want to roll out something that translates customer queries, natural language to SQL queries, and you're a SaaS platform, so you have customers that probably have privacy concerns, and like, okay, there's no way I'm gonna do this extra API call. In fact, my product is deployed on-prem. They're going to want to take something off the shelf and fine tune it so you have control over it. So in that case, that's where I think this graph is not very applicable, because you're not actually trading off task accuracy versus fine tuning. You're saying, I will go through that extra effort of fine tuning. Maybe I'll use LoRA, but I'm doing that because I have control over the sort of data, and it doesn't leak out over an API.
Yeah. And so maybe LoRA, and do you feel like LoRA is kind of in between the yellow fine tuning section here and in between kind of the few shot prompting? It's kind of like you've gotten as much as you can with prompting. You don't want to go build a whole other model. This is kind of that middle ground that you can go try. Is that kind of where you would place this? And that it's missing from Andrea Karpathy's image here.
Can you restate that? I'm not sure I quite understood the question.
Yeah, I guess where I see LoRA landing is in between prompting and full fine tuning, and that's kind of where it is. I think for me, what was really interesting is in the paper there were examples where LoRA actually did better than the base model because it was optimized for a specific task or a specific use case, and I think trying to understand what is it giving up? Are there things, because it's a smaller model, is there any kind of trade-offs? What did it give up to optimize for X task? Did you get any of that sense from the paper, or just kind of
Yeah.
intuition?
Yeah. So when we say baseline, we're not talking about like the baseline, like raw model.
Yeah,
What the authors are comparing was LoRA against existing like baseline fine tuning. So I think we're using baseline two different ways
got it.
here. So when I'm
Okay,
saying like baseline full fine tuning, it's the classic like I'm taking off the shelf model and I'm updating all the weights. I'm back propagating everything, all the weights. And what the authors were showing was that I don't need to was that LoRA performs better than that existing method. Um, and I'm assuming depending on what the and here I'm using baseline differently now, like the baseline foundational model. I think depending on what that is, it could perform better or worse. I don't think the paper, unless I missed that, has a comparison there.
got it. Got it. That is super interesting. Okay, keep going. I feel like I keep interrupting you on your
No,
on your.
no, no. We
This
keep the
is
question
really
going. I think I like that natural format. So um, well, we've talked quite a bit about the implications. So what is it? How can you represent it smaller and do that in a principled way? This is where I'm going to dive just a bit into the math. I'll try to keep it as simple as possible, but we'll start with matrix decomposition. So it's very simple. Like what this graph is showing is that if you have a matrix A, you can express it as a product of two matrices on the right being multiplied together. And if you see the K on like the Y matrix and the K on Z matrix, that's like how wide the column and the row is. And this is what in linear algebra terminology people call the rank of the matrix A. And I think for engineers and computer scientists here, you can think of A as a measure of how much information the matrix A contains. You know, the larger the K, the more information that matrix actually contains. Now, sometimes I think it's easier just to think about it from right to left. From the right, I can imagine I have these two skinny matrices. If I multiply them together, I get the matrix on the left. And again, for those of us in the audience that are more like from the software engineering background, this should immediately stick out to you because it will take way less memory to hold the information on the right, even though we're saying the matrix on the left is exactly the same. That is going to be the trick. So the question now, the key is when I'm talking about the update weights, this is not what it looks like on the right here, right? This is the full matrix. I want to get to this sort of representation on the right that is sparse, shouldn't use the word sparse here, but like has less memory footprint. So we were talking about matrix multiplication from the right to the left. Going from the left to the right is where we'll take our second mathematical leap. That'll be the only one, I promise, which is the technique called singular value decomposition. So in this, what we're saying here is you can take any arbitrary matrix, even our weight update matrix from this slide. We can decompose it such that the middle matrix, everywhere in that matrix is zero except the diagonal. And the diagonal has a very, very special property, which is the non-zero values on that diagonal tells you what this K value is. In other words, it tells you how much information that matrix contains. And the smaller that K value, the smaller you can make the representation on the right be. Okay. Any questions here before I move on to truly the final leap?
This is great. And yeah, folks in the attendees, feel free to drop questions or ask as well. This is great, Harrison.
So just going back to the paper, what I promised was as long as we understand what they mean by low intrinsic rank, we'll understand everything else. So the last mathematical leap is, okay, I get what a rank is. What's intrinsic rank? So let's dive in. So at the very top, we had our initial decomposition. Remember what I said was in the non-zero values of that middle matrix represents ranks of K. By the way, more importantly, in this decomposition, the K is, these singular values on the diagonal are sorted. And the larger the K implies how important the first column is to the final matrix, how important the second column is, and the third one, and so forth. So now, in this example, the yellow, like at the top row where my cursor is, the yellow box is 0. So there's no value there. This is K equals 2. There's no value there. You can equivalently rewrite the matrix on the left by lobbing off the last column without any loss in information. And that's how you get to the third one, right? So even from the top row to the third row, we've already compressed our representation by a factor of 2 without any loss in information. It's pretty cool, right? Now the final transition from the third row to the final row is what the authors mean by like low intrinsic rank. If I notice that, say the one on the bottom right is a low value, I can just pretend it's 0. I'll throw it away. That means I can lob off the third column of my matrix and achieve an even smaller representation of my original matrix with there's going to be some loss in how closely that resembles. That's why in the graph it's like M bar instead of M. And so, to reiterate, at the first 3 stages, you're lobbing things off, but there's no loss. At the final one, you are taking a smaller value and you're throwing it away. It's not the same matrix, but it's a good enough approximation. And this is the final graph I really promise this time, just to build some intuition of how why this should intuitively be true. That most singular values here are very low and are and implying that the matrix is intrinsically low ranked. So if I treat this grayscale image as a matrix, and I do the same technique where I, singular value decompose it, and I look at the singular values on the diagonal, that's what this blue line represents. You can see it really quickly exponentially drops off around like the 10, like rank equals 10. But there's still, 110 dimensions left. And what this graph is saying is you can probably lob those off, recombine the matrix, and you'll get probably something that really resembles the original image. And really all I'm saying here is I'm taking a long detour to describe compression here.
Yeah. I mean, sorry, go ahead. This seems like LoRA in one picture. I want to maybe go through this.
But that's it. That's LoRA in one picture. Is we go through all this justifications for why we can do this transformation, and ultimately at the end of the day, all the authors did was take the original weight update matrix and substitute it for this like 2 skinny matrices multiplied together that gets back the approximation. That's really it. I'll pause there. Any questions or?
So I think one of the things that the paper started with here, maybe I can start there, is like this, this looks really simple. This looks great. Well, this was actually pretty novel because in the past, earlier in the paper, they were talking about how prior to this, teams would add these adaptive layers to LLMs. And the con with that is obviously it introduces inference latency. So you have your LLM response, you have this adapter almost model that it
Yeah,
would go through. So you take the response, and then maybe the adapter model is like, make it better in some language
sure.
that the LLM wasn't good in, and then it
Hmm.
would reduce the inference latency downstream.
Yep.
And so what you have like super simply here is actually pretty novel though at the end, because this approach doesn't have that inference latency. It still gets you, whatever optimization you're trying to do on the
Sure. Hmm.
response.
Hmm.
Um, where does this break? Like maybe, I don't know if like, where do you feel like this might not work?
It's an interesting question.
Like, and I think that's one
Yeah,
area I'm thinking about after this paper. Like, of course, you're the paper authors, you're talking about, look at this, like it's
sure.
great.
Yeah.
But like one of the questions I had is like, well, great, why doesn't everyone use this?
Yeah. I
And
think so. There's two very interesting things I'll say about it. One
yeah,
is I think in hindsight, these things always look really obvious. And you're
yeah,
like, oh, all you did was like change the shape of the freaking thing. Like, why didn't I think of that? Right. I I don't know. I think really big innovations will often seem obvious. What I think it could break is this is a very simplified view of what happens. And if I double click into that weight update thing, it's not just a neat matrix. It's like there's this whole like transformer mechanism here, and there's actually multiple sort of neural networks working together to produce an LLM. And so I think where it gets challenging and where it might break is when you think about, well, where the hell do I put this adapter? Uh, so just okay,
if you pull up the paper, actually, there's a,
yeah,
maybe we can dive into like, there's like, I think it's like there's a section on like practical benefits and limitations. I think it's page 5. If you Okay. Yeah, right above the empirical
hmm,
experiments. Yes. Okay. So that last paragraph, which is like, has its limitations. It's not straightforward to batch inputs to
hmm,
different
hmm.
tasks with
Yep,
different A and B in a single forward pass.
yep.
I didn't totally understand that. And they didn't add a lot of detail on that, but like my interpretation, tell me if you agree with this, like my interpretation of this was that, you know, figuring out that A and B matrix that you got to, and
Hmm.
how do you, so if we started with just an example, let's say we were trying to make the LLM, we're trying to optimize for, let's just say a language, like a specific language,
Sure,
Armenian,
yeah.
probably one that they didn't have a lot of data on. And so you're trying to answer back to people in Armenian. Is it getting these inputs, figuring out in a single forward pass what, like I'm not totally sure how they, yeah, like I don't know if you have an interpretation of this.
I do. What they're saying is if you fine-tuned um your LLM on like the let's just use the SQL example again, and then
Yeah,
maybe have another one, which is I've also fine-tuned it to write pandas dot apply
yeah,
functions. Okay. So I've two versions of these. I have two fine-tuned versions.
yeah,
What you're saying here is, well, each one I have to attach this adapter to, and I actually think we should get into the details a little bit after this one,
yeah,
which is I think another practical limitation. What they're saying is, okay, let's say I figured out where to attach this adapter, but I can't predict. But if I have a batch of inputs that's both the SQL example and the pandas data frame example, it doesn't work. Like
mm,
each fine-tuning thing can only do that one fine-tuning task. I can't batch it together.
mm,
Um, and I think, and I'm going out on a limb here. I haven't read the other papers for the existing adapters, but I think the existing adapters did have some sort of fusion thing going on. We can have
mm,
multiple layers of the adapters, and then there's another thing that fuses them together. Um,
mm,
I can't help but view this from like, my background is in distributed systems, mostly in data engineering.
Yeah.
I tend to feel like these problems of if your input is multiplex and it has to go to a different model, I think there's probably easier levers to pull on the deployment side of more traditional distributed systems engineering than this limitation they're talking about here, which is, oh, the adapters can only work on one task, and if you have an input that's multiple tasks, it can't multiplex it. But you're right, it is a limitation the authors call out. I think the other limitation I wanted to go to was that we're like very simple or vastly oversimplifying here, right?
Mm-hmm.
And if we look at what's in the attention head,
Mm-hmm.
damn it. So the existing adapter methods will have you adding these adapter matrices on top of the feed forward, or on top of on top of either the feed forward mechanisms. But what the authors are doing, they're saying like, we don't know where to attach it. And let's just attach to some of the attention heads, maybe not others. And here's where things get super interesting. Okay, here we go. Just give me one more second to try and find these results. Okay, so there's this open question, like which matrices in the transformer should we apply? Is it the query? Is it the key? Is it the value? And you can see what they've tried here is, okay, what if we spent our entire parameter budget on like the query matrix, or our entire parameter budget on the key matrix? In the end, it turns out you just give it evenly across the query key value thing, and it's like the best. I think some of the limitations, it's like, it's yet another hyperparameter I have to tune is maybe the annoying part.
Yeah.
My intuition is people probably end up just spreading it evenly across all matrices, but that is another annoying part of this methodologies, that additional hyperparameter, if you ask me.
Got it. That's super interesting. I feel like I'm really excited to see if people put this into actually deploy this and use this. There's clearly some upsides. I don't have to retrain GPT-4. That's a big one. But it also sounds like there's I think the last one about the different tasks and batching, that's actually probably, to me, if just thinking from, deploying this in a product, if you're trying to balance 2 or 3 different things to fine tune on, you'd have to be really specific about what's the task that you want to optimize for. Maybe that's fine if you're focusing on the pandas thing, on specific language or specific, et cetera. Like maybe that is a fine trade-off.
I think it is. I think that the sort of like mixing batch things is, to me, maybe eventually more of how these AI businesses will evolve. A question more of how are they going to be evolved to be more vertical things. My personal bet on it is like the sort of, I need one model that's super generalizable, zero shot sort of across. That's gonna, I think that's always going to be in the foundational layer. I don't think you're going to want to get that when you're a business trying, assuming the thesis plays out, which is you have a lot of these small businesses that are fine tuning on top of these open source models.
Yep.
The one last thing I want to touch on, I want to make sure we get to, is just how much smaller the weights eventually are. The one that they've used in their benchmarks was 35 megabytes. 35. I mean, that I don't even know. It's like, okay, 10,000x. It's that
Wow.
much smaller. Now, it doesn't mean you can just download 35 megabytes and you have the model. It is, again, like an adapter on top of an existing one. But, zooming out from the mechanics of building models and reducing, it makes the ability to host these and share these, it's literally 10,000 times less the cost. And when we've seen this play out in every different sort of domain, right? Like you lower the cost of something, the friction of something, you get this sort of like 1,000 flowers bloom sort of effect. And I think that is why this is super exciting.
Yeah. Do you feel like most people like this is especially exciting for the open source set of LLMs? Is there any way, I guess, with like with GPT-4, you don't really, or 3, you don't really have, yeah, like where do you feel like LoRa will see the biggest usage of something like LoRa?
I think it's okay. What's the complement? The complement of LoRa is like a reasonable foundational model.
Yeah.
And I think the funniest thing about what like just going back to this like Vicuna thing, very impressive, but the compliments are like you can make a reasonable claim that they're kind of stolen-ish. You know what I mean? Like Llama was like leaked from Facebook. It doesn't have a commercial license. The data they trained it on using LoRa was like off of this site called Share GPT,
Yeah.
which is people posting their ChatGPT prompted responses. And so I think the latter, which is where you get the data from, is probably less contentious. You'll find things that where there's less of a gray area in terms of the legality of the data. And I'm not completely up to date on the latest in open source, but I do think that the complement and whether or not this gets even more adoption from open source more than it is already is the existence of really, really good reasonable foundation models to build on top of.
Got it. Got it. Um, so one last thing, and then maybe I think we're getting close to time. I think one thing we're hearing out, out in the Twitterverse is that people are stacking LoRa. So especially in the image space, you can stack one style and another style. And I think this is where Hugging Face is actually working with Stability AI on and doing that. Not totally sure how that works in all the
Mhm.
details, but any thoughts on that? Do you feel like that this might be especially interesting for image or other applications other than maybe LLMs? Than more text-based we've been talking about here.
Mhm. To be honest, I don't know.
Yeah.
I'm nowhere nearly as familiar with these models as they are deployed in the image space. Like, so the authors do make this claim that like, oh, we can go back here. One of the benefits is like, oh, it's orthogonal to prior methods. I'll tell you what the authors are saying, and I'll tell you why I think it's not. I don't know, like maybe it's not as impressive as of a thing. Is the reason why there's no additional inference latency is actually how the forward pass eventually ends up looking like. So it gets split. You have this other, the original embedding getting matrix multiplied by this A and B and then combined. So that's why there's no additional latency, because you can parallelize that part. And maybe I'll open another window here so you can compare it. And what they're saying is because we're using a different data path, you can also stack your original adapter on top. That's what they mean by orthogonal to existing adapter methods. I
Mm.
don't know if I don't know if that's going to be super useful. Like if you've gone through all this trouble of making sure you can get this down to reasonable size, or you can use another adapter. I I don't know. And I don't know how the stacking will work in the image space. I'm just not familiar enough to have an opinion on it.
No, that's I think we're all excited to see how this actually gets used in, you
Yeah.
know, so Harrison, this was super helpful. Thank you for breaking down the LoRa paper.
Yeah.
Thank you everyone for joining, and especially after the first chaos Zoom, I feel like I walked away learning a lot about this paper. So thank you
Cool.
all, and we'll do this again next week. Different
Cool.
paper, drop some suggestions, and we'll see you there.
Thanks,
Thanks.
everybody. Bye.